Good afternoon, this is Schweitzer, and we're moving into next one of a series of gas videos. And this one is going to focus on external factors. Now, external factors involving gases. We just got done talking about internal factors, so this is involving ideal and non-ideal gases, but let's look at more external factors. Now, all of this stuff, temperature, pressure, and we have not talked about volume, but that's pretty self-explanatory. So the most of this particular details here are just going to be reviewed. So over the next couple slides, if you find something that you want to maybe reiterate or add in here, please feel free to do that. Okay. But in this case, we have first thing to look at is again review what is the external factor of temperature, molecular velocity versus average kinetic energy. So make sure you understand that if we're comparing two balloons, okay, let's say one's got oxygen and one's got helium. All right, at 25 degrees Celsius. Okay, which of these two balloons has the same? What can we say about comparing average kinetic energy? Well, in this case, that's another way of saying temperature. Average kinetic energy, average equals 1/2 mass velocity squared. That's located right here. This is the average kinetic energy, which is simply the temperature. Takes into account both the mass and the velocity. This is the molecular velocity right here. Molecular velocity. Okay, that's how fast they're actually moving. Okay, so in this case, which balloon contains a fast-moving particle? This balloon contains a fast-moving particle because it has a lower mass. This thing has a molecular weight of 4 grams per mole, where this guy has a molecular weight of 32 grams per mole. Is this thing proportional? Not really, because we have this square here, but it is faster. Okay, real important idea here. Keep that in mind. All right, another example. How do we go about describing what this looks like? We take a sample of gas. You can read on your own and read the question. Which of these best describes this? Always pausing problems before we do them. And here's my answer. Right there. And this guy. Notice that inherently we just have longer lines. We haven't lost any particles. They haven't broken apart. We still have slow ones. We have real fast ones. But on average, they're moving faster. We have a Maxwell's distribution that we also used previously to kind of just show that. Alright. Pressure. Okay, now again, pressure, we talked a bit about pressure before. Okay. But keep in mind, there really are two ways we'll deal with pressure. We have atmospheric pressure, which literally is, you're standing right here, and you have all these particles with gravity pulling down on you and pushing on you all the time. If you were to go up to a hill, you would find that you'd have less pressure on you, lower pressure. So atmospheric pressure is really important as far as lots of properties of chemistry are concerned. We have pressure inside a container. Okay. Now, pressure inside of a container is produced differently. It's produced basically of impacts with a particle off the inside container of a wall. Keep in mind that the actual physics, pressure, is going to equal the force applied per area. Sometimes I'll make the analogy if someone hits you with the bat. That's probably not going to feel all that great. Okay, but in the old warrior days of Middle Ages, they knew this was a weapon and the people used it. So they decided to change it and they put little spikes all over it, and that using physics really changed the deal, right? Because with the same amount of force, but the area of this pointy thing is a lot smaller, so your pressure is much higher. So that's what we're doing here, is pressure. So forces are actually the number of collisions, okay, per area, which is really just the inside container of the wall. So a lot of times when we're dealing with pressure, we're dealing with the force, and we also reference the area of the inside container wall area. That really is important. If I cut this thing in half, the same number of particles, I have less the area of the inside container of the wall. And therefore I have more pressure because I have more collisions. For not traveling any faster, I just have more collisions. Alright, so again, kinetic molecular theory. I already kind of talked about this a little bit here. So what is kinetic molecular theory? It's a theory about moving particles. Okay, and a few things you want to just kind of have under your belt here. One, as the temperature is relative to the speed of the particle. So as I increase my temperature, I increase my speed. They're not exactly linked. They're not exactly the same thing. They're connected by the kinetic energy. Kinetic energy equals 1/2 mass velocity squared. It's not saying kinetic energy equals velocity. That's not what it's saying. But if this one goes up, this one goes up. Okay? They link. To create pressure, particle needs to collide with the inside container wall. So anytime you're trying to deal with pressure, if you're ever trying to explain pressure using what we call the kinetic molecular theory, you need to specifically talk about this guy right here. Collisions, more frequent collisions means more pressure. Faster moving particles means more aggressive or more forceful collisions. Forceful collisions, and that's important as well. So you think about this. What happens when I raise my temperature? Okay, the particles inside here move faster. Okay, so that's this guy right here. And how is that affecting collisions? Well, since the particle, the container is not changing size at all, I mean, if it got bigger, then it would be different. If it was a balloon, that would be different. But since it's not changing size, we have more collisions. And temperature-wise, they're moving faster, so they're more forceful collisions. So the amount of pressure on the inside container is going up because of both of these factors. This is the kinetic molecular theory. It's a non-math way of describing how particles act inside of a particular container. Alright, so here's an example. External pressure, external factors, pressure. So pressure is force per area, collisions per area, just kind of discussed this. Sample of a rigid container has a temperature increase from 25 to 50. Using principles of kinetic molecular theory, explain what is happening inside and happening to the pressure inside the container. Alright, again, we want to understand the idea that the temperature increased, so my molecular velocity increased. But really, when it wants to talk about pressure, you need to explain the fact there are now more collisions, okay, and more forceful collisions. Alright, now more forceful collisions, okay, will cause, in this case, more pressure. I'm kind of being brief with it because time is ticking on here, but, okay, that's what we want to talk about in a coherent manner. There's my answer. Okay, pressure increases, there's what we got. Alright, another example. Okay, how might you describe what the molecular velocity of an average kinetic energy of the two balloons above? Okay, so we got a little bit of a review here. Molecular velocity, okay, molecular velocity, average kinetic energy, these two are the same. And this one is faster. So this guy, they have the same pressure. Okay, these have the same pressure. I remember what you're talking about. I said more collisions means more pressure. If these are traveling at a faster clip, they're hitting the walls of the container more often. So why isn't the pressure here? Well, these are more massive particles. They have the same kinetic energy because they have the same temperature. So that being said, this guy does have a stronger velocity, but also has a lower mass. So it's hitting less forcefully. More often, less forcefully. This guy is hitting less often, but more forcefully. Together, they have the same kinetic energy. They produce the same net pressure on the inside of the container. All right. And we'll stop there for today. This is, again, kinetic molecular theory. Okay. One thing I also might want to point out about a balloon, and we'll talk about this in a second here, but a balloon, really, we have a pressure inside equals the pressure, and we have pressure outside.
Some might say that the inside's bigger than the outside because it pushes the balloon out. But in reality, when we think of kinetic molecular theory, its pressure equals collisions per area. So when I expand the balloon, the area increases. And therefore, my pressure inside my balloon drops as the balloon expands. And essentially, minus the elasticity of the balloon, the pressure on the inside actually equals the pressure on the outside. If the pressure on the inside was larger, then the balloon would expand, increasing the area until the pressures once again were equal. As long as the balloon's not changing size, we typically think about the two pressures being equal. And we'll see more of that on the next slide. We'll look at types of containers and some mathematics. Thank you very much.